So hello everyone, welcome back to my channel, and this is going to be an introduction to NLP fundamentals class. So you know, uh, nowadays generative AI is all the rage. You've probably seen ChatGPT, Claude, Llama 3 is all the rage right now, and you must have seen some demos or seen these models live in action. But what it fundamentally is natural language processing, and we will, through this series try to delve deeper into the very fundamental concepts. Let's trace our steps back and see how we got to generative AI. So let's dive right into the tutorial. So out here I have some notebooks, blogs, for you, which I am going to use to build your intuition, know about the fundamental concepts, see some code, and let's try to understand some of the very fundamental concepts of natural language processing. So let's dive in with tokenization. So I'll build some intuition around tokenization. It's the process of breaking down text into smaller parts called tokens. Very simple. These tokens can be words, phrases, symbols, etc., which are meaningful for processing text. So uh, when you see large language models in action, you must know that they do inherently use the process of tokenization. You may or may not know that, but you can see right here is the OpenAI's tokenizer, which they use, for GPT 3.5 and GPT 4 models. So, as they note, it's important to note the exact tokenization process is variable between the models. But, this is good for understanding how the large language models process text using tokens, which are, common sequences of characters found in a set of text. These models learn to understand the statistical relationships between these tokens and excel at producing the next token in the sequence of tokens. So if you come right here, so I have given it a sample sentence like never gonna give you up, never gonna let you down. Anyway, I'm probably very horrible at singing. But yeah, so the GPT's tokenizer has, broken this input text into some chunks which are called tokens. So it broke this text into 13 tokens. We had 50 characters, never gonna give you up, exclamation mark. And out here, as you can see, G is a separate token, ONNA is a separate token. So GPT inherently uses these tokens to sequentially predict the next best token and generate a sentence for you, which is pretty cool if you ask me. And if you look at token IDs, all of these tokens are essentially mapped to some numbers, and these are those numbers. And you know what, these numbers are what essentially at the back end of the GPT happens. It's just a sequential predictor. It keeps on predicting what happens next based on some very complex mathematics in inner workings, which we will go as we dive into advanced natural language processing. But for now, I think this is gonna do. And maybe just for fun sake, you can just open your GPT window and type this text and just see for yourself what it produces. So anyway, that was some deviation from what we were trying to do. So here are some fundamental concepts. Tokens are the smallest units of text that carry meaning. Tokenization is the process of splitting text into tokens. It's a fundamental to prepare text for further processing like parsing, indexing, feeding into NLP models, just like GPT, like we saw with the tokenizer. So anyway, this is a very, classical approach of, tokenizing your text as you have it here, never gonna give you up, never gonna let you down. So first we import NLTK, which is Natural Language Toolkit, and it has a tokenization method, a word tokenize method which you can import from the tokenize package. And here's the example text. And we initialize tokens is equal to word tokenize. We pass the text into it, and then we are able to print the tokens here. So yeah, pretty much it. That's how it's prepared these tokens. So currently these are not mapped to any numbers or anything like that. This is just a tokenization that's been done over here. So it's definitely different than what GPT did, but that's how it was trained to do initially. Anyway, next concept is lemmatization. So why don't we start by building intuition around it? So lemmatization is the process of reducing words to their base or root form, right? So for example, you may have the word kites, babies, dogs. So the base or the root form is, kite for kites, babies has the root form of baby, dog, and so on and so forth. That's how English language is structured. So lemmatization is a fundamental concept in NLP. The base form of a word after it has been reduced to its inflected forms is called a lemma, and lemmatization is a linguistic process of reducing words to their lemma, taking into consideration the morphological analysis of the words. So all of these methodologies, morphological analysis, have become very, very complex in today's date. But for now, we will see how the fundamentals were implemented when NLP was in its nascent state. And explanation is right here. Emblematization involves understanding the morphology of words. It often requires a dictionary or a lexicon and can include complex algorithms to correctly identify the lemma based on the usage of the word in a context. Right, so NLK from the same library we import WordNet lemmatizer. That's one of the lemmatizers we use, and lemmatizer.lemmatize word for word in words, and we print the lemmatized words. So you see that the base form has been achieved. Driving should have been drive and smiling should have been smile. I don't know why it failed there. Maybe it wasn't trained for it, or the lexicon, as that was mentioned, wasn't proper. Anyway, feet becomes foot, so on and so forth. So let's move on to the next concept or a methodology, which is bag of words. So let's build some intuition around it. So bag of words model is a simple yet powerful way to transform text into numerical features. So we are gradually building to what happened over here. We had text represented by numerical data. So bag of words is one of the ways that it used to be done or is done in some specific implementations or problems that require that. So it involves representing text data as a bag of words, a bag which has words, a bag of words. I don't know, I'm probably being lame, but it's a bag and it has words in it, ta-da. I should probably have some confetti on the screen. Anyway, so bag of words model disregard the order but maintain multiplicity. Let's dive into the fundamental concept. A bag of words model, a way of extracting features from text used in modeling, such as ML algorithms. It describes the occurrence of words within a given document. So this is where we introduce the concept of vectorization. So it's the process of converting text into numerical vectors based on the frequency of each word present. That's interesting. So I don't know why I've written vectorization and not given a space here, but that's a typo. I hope you can excuse me for that. So each document is represented by a vector. Let D be a document consisting of words, W1, W2, so on and so forth. Let V be the vocabulary of the corpus with words V1, V2, so on and so forth. Each dimension of a vector corresponds to a word in V, with the value being the frequency of the word in D. Lots of maths. Anyway, so the way to do it, I've used sklearn over here. I've imported count vectorizer. So this is some sample text I've given over here. NLP is interesting. Machine learning applies NLP for various tasks. So we initialize the count vectorizer here, which we had imported. So we fit and transform the text. So bag of words, we make an array of bag of words, vectorizer.fit transform texts. So here's it printed. So feature name applies for interesting is learning machine NLP tasks various, and here is the bag of words matrix that represents these particular features. So this can be a little complex, but what this essentially does is extracts features from text, features which can have some inherent meaning. for humans. We can put those interesting things into a machine learning model, and as a result, you will have a bag of words matrix. Very simply put. And each dimensions of a vector, of a word in V, will always correspond to a word in V, with the value being the frequency of the word in D. So D is the document with your all of the words corpus, and every dimension of the vector that we create V will correspond to a word. So that's what we want to do. So this is a very simple way of vectorizing it. This you see sort of a binary classification, ones and zeros matrix, but we know our models in today's date can even infer context, the context in which a word was said. For example, you may say the bank was robbed, and it's very peaceful near the river bank. So if you had let's say bank as a dimension, and nature as a dimension, so the value of the vector for bank in English language will depend on where it is used in a sentence. So if it's used in a sentence like I find it very peaceful near the river bank, so it's more likely to have a higher magnitude for nature, right? And if I say the bank was robbed by the robbers, led by the professor, of course, so it will be more in the likeness of bankness, if that's a word. Anyway, so that's some intuition about vectorization. So now we come into embedding architectures. Embedding architectures transform words into continuous vector spaces where semantically similar words are mapped to proximate points. So let's dive into it. I will explain this. They capture the deeper linguistic context and relationships between words. So this was essentially like a binary, interesting features extracted, all of the features that came out of here, and created a matrix which was a very simple, doesn't have context, doesn't have anything. It relies on frequency being a measure of importance, or yeah, just like that. But embedding structures are much more complex. They have word embedding, semantic similarity, and let's explain some maths over here. So word embeddings are learned in a way that words appear in similar contexts, have similar embeddings. So there's an entire paper on embedding architectures. Maybe you should look at word2vec, which is what I am trying to do over here. Maybe we can even try to look at its scientific paper. I would definitely leave it in the links. But anyway, so here's the mathematical explanation. So it involves constructing a neural network model that predicts a word based on its context, or vice versa, and using these predictions to learn the embeddings. So the embeddings, or the vectors in this case, are definitely learned by feeding in a corpus of text, making it understand which words are appearing in similar contexts, and accordingly applying mathematical values to vectors in hyperspace, and have them be representative of some meaning which has similar semantic words you will find in similar directions of let's say vector. Anyway, so let's look at this graph over here. So this is an example of tense, and this is an example of male female. So very often these vector spaces will have very high dimensions, as high as 768, sometimes 1024. So very high dimensionality is there. So let's consider this male female example of vectorization. Let's say this is a vector space. So king and man are definitely different on this particular axis. So this can be an axis indicating more specificity to a role of a person. Let's say a king has a different role than a normal man does. So king is definitely higher in this direction as compared to man. Let's consider this particular direction, right? Or maybe not. Let's just consider this one. So king and man are more to the left side of this particular axis. if we draw the coordinates, they are definitely more towards here, whereas queen and woman will be somewhere here. They'll have maybe the same coordinate on this axis, but definitely, as you can see, they are over this axis. So this axis can be a representative of maleness and femaleness, right? So as a result, when you vectorize these words with respect to the origin, they get different positions with their position and magnitude even representing where representing a particular semantic context, right? Similarly, for tense, this particular axis could be a measure of past, future, right? So, or even present continuous for that matter. But yeah, so this is more towards the present tense, this is towards the past tense, and if you extend this, you may even have something like will walk, I will walk tomorrow. So will walk will be somewhere here on this axis. Yeah, anyway, so that's an intuition and explanation behind embeddings. Let's see some codes. So I've imported word2vec over here, which is a popular vectorization methodology which has been used. So LLP is fun is the sentence, deep learning drives NLP. So we initialize our model. So this definitely has some parameters which I won't go into now, but definitely I'll create another video covering it. So vector is this, and we print the vector for NLP in particular with respect to this text corpus. That's how it's represented, and of course it's in scientific notation. It's 9 into 10 to the power minus 3. It's very hard for one to understand. I wish I had printed the length of this vector. That might have been interesting to see the dimensionality of the word2vec model. But yes, that's your intuition and introduction to NLP fundamentals. Thank you for sticking with me. I think this has been a fun journey for me. Let me know how I can make it better, and definitely this is the first draft, and I'll be making this a lot more. So yeah, life is fun.